Hello. Today I'm going to add some vectors for you. The example I'm going to use is the one that is on the first slide of your vector addition practice for today. It looks like this that you can see right here. I'm going to add vector A to vector B. Now, if I wanted to write out what that would look like, the problem I'm trying to solve, I would be asking for the resultant vector, which is the sum of vector A plus vector B. So that's what that would look like if I were going to draw that out. So remember that any resultant answer requires two things, right? The magnitude and the direction. And by direction, I mean the angle based off of some axis. So please remember to always include both of those, otherwise you'll only get half credit. So real quickly, I'm going to go ahead and add these two together using the parallelogram method. So over here, I'm going to do the parallelogram method. I know it's not everybody's favorite, including mine, but we'll deal with it. So here's how I do it. Notice that vector A goes from 0, 0, up 4, and over 1. And so over here, I'm going to go start at the head of vector B and go up 4 and over 1. So 1, 2, 3, 4, over 1 right there. So I should end up right at that point. So if I were going to pick up this vector and draw the same size and a parallel line over on this side to create my parallelogram, it would look like this. Like so, roughly. Yeah, you get the idea. I can do the same thing with B, and then I can go over 5 and up 2. So I go over 5 and up 2. Yep, I end up in the same point. That's a good thing. So it looks like that. And then my resultant vector R looks like this. Like that. And you always have to draw the arrowhead in there. So that's vector R right there. That's my resultant. That's what I'm trying to find out. So one thing that might be important for you to recognize is the fact that you should be able to know where its final location is, where it's the tip of its arrowhead is located. And so I think you'd agree, it looks like it's at 6, 6 right there. So I'm going to go ahead and write that in there, 6, 6, because we're going to use that in just a minute. Okay, so how do I find the length of or magnitude of the vector R? Well, that's pretty easy. I use that Pythagorean theorem. You may remember from your algebra class that you can take the square root. I'm going to write it over here just so you can see it. So the length of any vector, so the length of any line, I should say, is equal to the square root of y2 minus y1 squared plus x2 minus x1 squared. And so for us, our x1 and y1 are both 0, and so they go away. And so you can see that I have 6, 6 right there. So that's our y2 and our x2. So 6 minus 0 squared plus 6 minus 0 squared. Okay, so what I end up with is something that looks like this. 6 squared plus 6 squared, or the square root of 72, which is 8.5 units. I don't know what the units are. It doesn't really matter. It could be meters if it's displacements, or meters per second if it's velocities, or meters per second if it's accelerations, or newtons if it's forces, or kilogram meters per second if it's momenta. Whatever. We'll get the idea. So I'm just going to use generic units right there. Now here's the trick. To be able to find the angle, I always have to measure off of one of the axes, because the axes are recognized by anyone in any system. And so how am I going to measure off of the axis? I don't really have an angle that goes all the way down. But in reality, I do. I just have to think about this in a slightly different way. So check this out. You just said that that point is 6, 6. That means that, I'm going to use a blue pen here so you can see it. That means that it goes over 6, like so, and then it goes up 6, like so. Now what does that look like? We've got this leg and that leg and a hypotenuse. That looks like a right triangle. And really that's what we used here to find the 8.5 units. But notice that the horizontal is the place where we want to measure from. So if I wanted to measure the angle right there, I want that angle. Now, I prefer to measure all of my angles away from the x-axis, you could measure off of any axis you'd like, either the positive y or negative y, it doesn't really matter. You can make this north and east and west and south if that's appropriate to your problem. It doesn't really matter to me. As long as you measure off of something that everyone will recognize, and everyone recognizes the positive x-axis. So I'm going to go ahead and do that. Now remember, this side is 6 and that side is 6, and so you might remember that the tangent of an angle, theta, and that's really what we're trying to find there, angle theta, the tangent of the angle is equal to the opposite over the adjacent side. So if I wanted to, I could do the inverse tangent. That's to go the opposite direction of the opposite over the adjacent, and that should tell me what theta is. It's the equivalent of what I used to have to do when I was a kid, and that was to go in the back of the book and use the table in reverse to try to find what the tangents were. Super annoying. Be thankful you have scientific calculators now. Anyway, yes, I'm old. Anyway, so the inverse tangent, easy enough. Inverse tangent of 6 over 6, which is the same as 1, is equal to 45 degrees. You probably could have figured that out logically anyway, just knowing right triangles. So 45 degrees, it's 45 degrees, and then you have to tell me what axis you measured from, and in which direction it is off of that axis. So I will say up from the positive x, because I don't really have any other ways of describing it at this point. Okay, so that's the parallelogram method. I'm going to erase some of this so I can talk very quickly about the other method. That other method is the component method. I think the component method is much more applicable and much easier to use. So bear with me here for a second. Okay, let's look at vector A. Wouldn't you agree that the vertical part of vector A is just going up 4? So I'm going to write that like this. AY, because that's vertical, right? Could be up or down, is equal to, now it's up, so I'm going to put a positive, and 4. Now AX, which is the horizontal, right? So it could be right or left, is only 1. So I'm going to go ahead and write AX is equal to, and it's 1 to the right, so I have to put positive 1. Hopefully you're with me so far. Switch colors here. Okay, let's do the same thing for B. BY is just going up 2 right here. So B sub Y equals, and it's up, so I'm going to use positive 2 right there. B sub X goes over 5. So B sub X is equal to positive 5. Positive because it goes to the right. So now I can go ahead and take that information and use it by grouping together those things that are like terms. So it may seem like these all have the same units, but remember that these two, A sub X and B sub X, are both horizontals, and A sub Y and B sub Y are both verticals, and so they're different things. So we want to group the horizontals together and then group the verticals together. And so we end up with this. If I wanted to say something like this, I could say the horizontal for our resultant is equal to the sum of all the horizontals. So A sub X plus B sub X, or let's see, plus 1 plus 5, or positive 6. The verticals is equal to the sum of the vertical components, so A sub Y plus B sub Y, which is the same as saying positive 2 plus positive 4. I did that in the wrong order, but you'll get the idea, equals positive 6. So now I know that the location for the resultant, for the tip of the head of the resultant, is actually right there at 6, 6. Right there. And so if I wanted to, I could draw that out like so, just like I had it before. And then I use the same method. So I use the Pythagorean theorem to be able to figure out what the size of it is. 6 squared plus 6 squared. And that gives me 5.8 units, just like we had before. And then I use the inverse tangent again. So theta equals the inverse tangent of 6 over 6. And it's again for the same reasons. 45 degrees up from positive x. Okay, hopefully that makes sense. Again, the back half, the bottom half of your math problem, you're actually finding the answers, done the same way either way. So you use the Pythagorean theorem and the inverse tangent. And the cool thing is, just a real quick aside, if you always use the component method, then you're going to have r sub x here and r sub y here. And it's going to they're going to combine together to form the resultant, like so, r. So if we always want to find the angle off the horizontal, this is why I prefer the angle measured from the horizontal, theta. Look what we can do. This always works if you do it this way, and you always measure from the x-axis, the positive x-axis. You get the tangent of theta is equal to the opposite over the adjacent, r sub y over r sub x. So the inverse tangent of r sub y over r sub x will always, oops, there we go, will always give you the angle based off of the x-axis. So that angle is the one we're looking for, and again, it's based off of that positive x-axis. So that's why I use that. That's why I prefer the tangent for this method. Hopefully that helps. Good luck. Do your best. Make sure it gets submitted by the end of the period. I want to see where everybody's at so I can figure out how to fix things for next week. Thanks. Have a great weekend.